Okay. So here, the type of thing that we are interested in is to understand, what is the largest power of a prime, largest power P that divides, a number of the form x to the n minus 1. Okay. Obviously, there will be some more conditions, but this is what we are interested in understanding. Okay. So, for example, we have begun to understand this, so we understand that x minus 1 divides x to the n minus 1. Do we all understand this? Okay, right. So this can provide you with a method to find prime factors of x to the n minus 1 for a number like x to the n minus 1. Okay. So let's begin with that, maybe that the fact that let's try to apply this result first to find prime factors, and then we can extend to find, okay, what is the largest power of a certain prime that divides? That will be a more generalized question. So first, let me ask this question. So find at least 5 distinct, this is a 5 distinct prime factors of, let's say, 3 to the 120 minus 1. Okay, let's begin with this. Then we can ask more specific questions. So find one you can tell so that we can start listing them out. Okay. So, just to clarify this, I'm not sending any more mails for classes anymore because the timings are fixed. I think that's better. Overuse of email is no good. Okay. So, yeah. This can be an interesting question, right? Find at least 5 distinct prime factors of 123 to the power 120. Yeah, no, not just any. So did you say even power of 3? Any power of 3. It's not about even or odd, right? Yes. Yeah, that's what you said is not incorrect, but it's, yeah, right. So certainly 2 is there. So just So 2 is always there. This is an even number, simply. But can we, are there 5 more? No other, so you cannot find any other prime factors? Hmm. Why do you say, okay, 5? Okay, why? So we have done some theorems earlier. So this problem, it doesn't need any of those theorems. But we had done some, right? A to the power p minus. Okay, let me just write that. And if you can use that, though we do not need that, but that you could use. I was expecting that if you can, you would end up using it. We had done this. So maybe Aparna, with this, you could confirm that 5 is a divisor. See, try, think. 5 is certainly there, but it has to be confirmed by some argument. And yeah. So you guys know that, I mean, you know that this thing just means that p divides a to the p minus 1, right? That's the utility of this in this context.
I'm not sure.
Hmm. And so that gives you 5 as a prime factor. Does it? Let's see. Think. But how? Yeah, that gives 5 a chance, but you have to explain. That's another way you could approach. So what powers of 3 end in 1? That's another thing you can think. Hmm. Sorry. So why is this true? Say that you mean the quotient. Yeah, that is correct. Yes, that is correct. Yeah. Yeah. Certainly. So that's another way of explaining it. Yeah. And this is the most elementary way. And yeah, that after every fourth power, what you get is something that ends in one. And you can always explain that, like, okay, this ended in one, the next one ends in three, the next one ends in nine, the next one ends in seven, and again ends in one. And it continues. So with that, you could say, and is this point though, but this is a more general statement. So is this point clear to everyone? That 3 to the 4 minus 1 would divide this? Yeah, this should be clear. No? Okay. Sorry, did you say yes or no? Yes, yes. Oh, good. So then it's easy. And it's basically that, I mean, this is the, you see, just change what the x is, right? I don't know what becomes 30. Yeah. And so basically this becomes your x, right? Obviously, Ishana has given an explanation when you divide and so on, what happens. That's good. And it's basically just this. You just have to manipulate the thing. Yeah. So based on this also one can say, yeah. When and basically this one can be is very interesting because this one basically says that x to the nm minus 1 is divisible by x to the n minus 1, right? So I mean any divisors of this power, that to the power 1 minus 1 will divide it by the same reason. So this is the thing, another thing. Okay, but let's not try to remember these things. I mean that you observe and you do, not important to remember. And but this small example we saw. So can anybody also just can conclude from here because this is in a slightly different spirit. Yeah. So well, why not? I mean, a to the 4 minus 1 is divisible by 5, right? Which means that 3 to the 4 minus for any a, right? It's a more powerful statement. 3 to the 4 minus 1 is divisible by 5, and that means, but it's a trivial statement. Okay, so that's the point, right? This is like a trivial statement. But yeah, so basically what we said earlier, I mean, is the more important thing that this is. Yeah. Hmm. So that's one way to see it. But basically, another way to see that this kind of thing is, well, you can say the 3 to the 4, this is just going about the same thing. This is 1 mod 5, right? And because it's a trivial statement or Fermat's little theorem, but then you can, and this is the thing, what you do, like what I wrote about that divisibility statement, right? That x to the 4 minus 1 divides, let's say, x to the 40 minus 1, yeah? And we gave some explanation. All fine. But what I'm trying to say is that it becomes a natural operation if you use the language of congruences. What is that natural operation? Is that what is that you can raise both sides to the same power, right? 5 and 5. And this becomes 3 to the 120, and this remains 1. You see, do you guys see the difference, right? Something that you already know and you can explain and you can prove, which must be done in the case of congruences also. But the language of congruence is built in such a way that that fact, what is that fact? The fact, this 3 to the 4 minus 1, again, just saying the same thing, but notice this, notice what is happening. This is maths, right? That you say this thing, I mean, you can observe this thing by several ways and so on. You can give explanations. But using congruences, I'm not saying that the proof becomes any simpler, but the statement becomes the statement, the language of congruence is such that the statement becomes analogous to the statement in equations. In the case of equations, that is, you can raise both sides to the same power. Do you see the subtle difference? Something which is true remains true. I'm not saying it becomes easier to prove. Maybe it does become easier to prove. That's a different thing. But the statement in this language becomes a more natural statement, or becomes a statement which you're more used to, becomes a statement which is true in a simpler context. And this statement becomes analogous to that trivial statement that you can raise both sides to the same power. That is the effect of making nice definitions, nice notations. That is the effect of doing all this. That's how you develop new insights, you know, in new places by using an old language. Right? This is like an old language of raising both sides to the same power, but now it has a consequence like this, which is something new. Okay, that's a subtle thing. Okay, but either ways, the point is that we know that it's not true. Okay? So we found, okay, now let's try to find more factors. Let's keep going and see if we can find more factors. Okay, so since you, okay, you are saying, so let me see if other people, so now I want someone else, meanwhile you can find other factors. If someone, Aparna and Pragdish, if you can explain, even if you can explain why 7, so you explain why 7 is, no. 3 cube is 1 mod 7, is it? 3 cube is 27. No, 3 cube is not. Yeah, yeah. 3 to the 6 is. Yeah. Uh, is it? Yeah, 3 to the 6. Since it's minus 1, 3 to the 6. Okay, good. And again, you see, congruence is, even if I make a mistake, I mean, just like if we write this, then we would know how to find the power. But either ways, you know that for Fermat's little theorem also, but just by computations, you understand. So 3 to the 6 just raising, again, congruences do it for you. And then obviously you can raise both sides to the power 120. Okay. So that is one way to see these things. Okay, there are many elementary, non-elementary, but this is sorry, it's whatever it is, 20. Yeah, 7 works. Okay, 7 also works. You can see it in this way, or I would suggest that it's just better. So let me say it in a more elementary way, similar to what we did for 5, like the powers and so on. What the suggestion is in these cases, and sometimes this is interesting thing to do, is to just basically write this number in different ways, right? Writing this number in different ways. For example, you had 3, then next step you can try to say, look at this and see if it gives you any new factors. Then you can look at this and see if you get any new factors. For instance, what we did now is we looked at this, and then what is this? 3 to the 6 is 729, right? Yeah. And then this is divisible by 728, right? Because that's what we know, right? That's what we started with, right? That this, basically I'm saying that only from this you can write the number in different ways, and you can understand. Okay, this is the suggestion. This is what I had in mind initially. If you don't use any theorems, any congruences, basically you write that big 120 in different ways and you find different factors. So can you tell me, if you write it in this way, do you find a new prime factor? If you use this, do you find a new prime factor? 27 to the power 4. Do you understand this idea? This idea could give you potentially new, or whatever. Let's try. Yeah. Yes, 13. You see, it gives you 13. Yeah. So let's. I was thinking of one thing here. 1 minute. Yes. So try to find the other one more. to begin with. I mean, there are many others, I suppose, but I was thinking something. Yeah. I mean, okay. I was just saying that you could also see it by congruences. That's okay. Yeah. But just this is a way. 13. Is there some other prime factor which you can tell? Ah, you found 11. So how do you find 11? Ah, something. No, 2, 20, 12, 12. 12? Yeah, 12. So what does this give you? Uh, 3 to the power 10 is 1 mod 11. Yeah. So obviously, this is a more powerful technique. It already gives you results without computing. But yes, that's right. This is 1 mod 11. You could check it in any way, either directly or you can just use that theorem. You see, you find all these factors, and maybe you can find more. Okay? And also, what we somewhat gather is, I mean, there are like the more composite this 120 is, there are more primes. It will tend to have more primes. No, nothing. I don't know anything more than that, so I cannot say. But yeah, okay. So that is there. So that was a decent small exercise. Now I want to move forward. Now we can look at these primes and we can ask um, about their squares. Yeah. So let's ask this question. Okay. Does 5 square divides 3 to the 120 minus 1? If you like this question. 5 square, does 5 square divide 3 to the 120 minus 1? Okay. Think about this. Okay. I'll just be back and drink some water. So does 5 square divide 3 to the 120 minus 1? No. Okay. Why? Okay. Why? That's an interesting statement. So you're saying that 5 square cannot be written as 3 to the k minus 1 where k divides 120. This itself is an interesting statement, whether it implies that, but why is this true? Okay, right. So you're saying that this can never happen. This is an interesting statement that this can never happen, and it's obviously easy to check, as you said, just check. But now here is a very interesting thing. What we are missing is now we are beginning to think that all factors of 3 to the 120 minus 1 occur in this very nice and canon natural way. That is not, why should that be the case? Not all factors of 3 to the 120 minus 1 are of this nice form 3 to the k minus 1. This is what polynomial theory is giving us. But numbers are much more random in the sense. Do you see the point? Does everybody understand this? And Ishana, do you see the point? This is not all factors. Yeah. So just because 5 square, okay, just because 5 square cannot be written like this doesn't mean 5 square is not a factor. It could have all kinds of other factors. Yeah. For the same conclusion, you're saying no? Okay. Hmm. Hmm. Huh. Hmm. No, 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 no. Okay, so let's check those powers because this is an interesting approach. This is approach using which will show us the strength of Congress. Let's see. So basically, we are now interested in what is 2 to the power 40? What remainder does it leave when divided by 25? What is it modulo 20? Let's take this a little slowly and see. Hmm? So, well, so let's this first, as you said, we check the first 5 powers. So we have 2, and then we get 4, 8, 16, 32. 32 is 7. But what I don't understand is from here, how can you conclude that 2 to the 40 cannot be 1? More cannot leave remainder 1. We want to know if x can be 1 or not. I hope everybody is on that page. Or maybe let me not write x. It can get confusing with the other notations. Let's just write r. We are interested in knowing whether r is 1 or not, right? That's the whole point. Then 3 to the 120 will be 1. But from here, how do you conclude that 2 to the 40 cannot be? It can be. How do you know it cannot be? can be. So far, we don't know. Think more. This is what you have to do. Or, I mean, if you are interested in the congruences approach, you can go and try to actually find 2 to the 40. What is it? Somehow you can find, I am sure. If you go with that approach, you can find what it is modulo 25. What remainder does 2 to the 40 leave? If you want to try that approach. Try some other approach. It will not be difficult to calculate 2 to the 40 modulo 25 will not be difficult. Especially with this powering idea that we have, right? That is 3 to the 120. If you can reduce it to 2 to the 40, and all of us follow it, you could use that idea to calculate 2 to the 40 without taking 40 steps. Yeah. No, if it ends in 6, so what? It could be, it means it's divisible by 5, right? I think in Sunday's class, at the end, we did something like this, right? Where we tried to argue. So we know that 5 divides 3 to the 120 minus 1. Now, if we want to ask if 5 square divides 3 to the 120 minus 1, right? If you want to take the other approach, the congruences approach is there. But if you want to take the other approach, that is the same as asking if, you know, if 5 divides, so what was the, I mean, yeah, so it really depends on how you say it. Yeah. In the, no, yeah, because this 3 to the 4 was the key, right? 3 to the 4 was, so my point is that to the way we concluded that 5 square divides this, 5 divides, not 5 square, 5 divides this, the way we concluded was like this, right? And this we know. And so to say 5 square divide this or not, I mean, this is the same question. You just divide by the 5, right? But you instead don't divide by just 5, but you divide by something, the natural thing through which you got the 5 as a factor. right? So whether 5 square divides 3 to the 20, 3 to the 120 minus 1 is the same question whether 5 divides this thing or not. Okay, because it's not about 3 anymore, right? It's about 81 to the power 30. That is how we see it, right? It was really about 81 to the power, the natural place in which you found the 5 for the first time, right? Is this. And therefore, it makes sense to reduce the question to this if you want to try this approach, right? Obviously, 81 minus 1 is just 80, and 80 has only one 5 in it. So it doesn't change the question. So you're basically removing one 5 and some other things. But the key is you're removing a natural thing, right? You could ask that question. But I think easiest is for now is to just calculate 2 to the 40. Come on. So you cannot calculate 2 to the 40. What is 2 to the 40? Mod 25. So you can begin with some simple things, right? So you can take 2 to the 4. 2 to the 4 is, okay, 2 to the 4 is 16. So 2 to the 5. 2 to the 5 is okay, right? 2 to the 5 is easy. That is something that you can do, right? It's just 7. And now the question just reduces further, right? You go and you do 7 to the 8. How difficult can that be? So please calculate this. Please calculate 7 to the 8 mod 25 and see what comes out. So 7 to the 8 modulo 25. Yeah, 7 to the 8 modulo 25. You can just calculate it, right? Why is it? I don't understand. You can even just calculate 7 to the 8. It's not very big. If you, but you don't have to do that. That's the point. And so I don't know. So tell me, so what is the problem in calculating 7 to the 8 modulo 25? Because take some time and calculate. Let's see. So you say what you have, what is the calculation? You calculated the actual 7 to the power 8. 576. No, no. Okay, that is not in. Okay, no, no. But why do you have to do? I mean, that is so. You see, the what we are doing, right? We calculate the small power, and then because see, when you calculate the small power, the remainder again becomes small, right? It becomes less than 25. Even if the power is more than 25, the remainder becomes less. So you calculate the small power and you build on that. That is the way. I mean, you cannot calculate. You have calculated, but no, no, that's okay. But see this. So 7 square is what? 49 minus 1. Yeah, that's a good thing. If you don't do -1, you do 40, you do write 24, and then next, it's not like -1 is some magic. Okay, you write 24, 24 square is 576, that is 1 more 25. That way also you can see. But yeah, this is easier. And so you know that 7 to the 4 is 1, right? You see, this is how it, yeah. And so it is indeed 1. See, this is why congruences are there, right? Because we are interested in the remainder, and the remainder is not so hard as we think. The remainder is less than is a small number. It's less than 24 to begin with. That's where it's easy, right? And so on. So you get 7 to the 8 is 1 more 25. And basically, we understand then this 3 to the this thing is 1 more 25. And so the answer is not no. The answer is yes. Okay? This is a very interesting question for me, at least. Is you know that this x to the n minus 1 has x minus 1 as a factor, and so from there you get 5 as a factor. But then you ask, is 5 square going to divide? Is 5 cube going to divide? That kind of questions. Those are the kind of questions. What, because we are done with, I mean, the sort of small things we are doing, right, on prime factors. Now we want to know the multiplicity. Okay. So answer is yes. But this was sort of a random, it was calculation, right? We don't really maybe learn much from we learn the techniques to calculate. But now we would like to learn something from the final result, if we can. Do we learn anything? We don't know. Let's try the same thing for 7. Yeah. And maybe then slowly we can begin to see something. Okay. So here the answer is yes. Okay? So it's this. So let me keep it like this, and also a little bit more I'll write, which maybe help us to compare. But let's just keep it there, and let's just do the same thing for 7. Let's calculate and calculate. Okay. So yeah, same question. So just to recall, the way we found this was, I mean, I'm not saying the way we found it, but I'm just saying that what resembles this more directly is this. This is what we know. So you can do the modulo 49 calculation, and that's certainly a way. So, I mean, it does take a bit of calculation for us for now, but it's because we are missing certain results which we have discussed earlier, or maybe we have not done them enough so as to put them to use directly. But there are better ways, and there is something also general that is happening behind, using which you can say 5 square would have divided. So good things are there, but one has to go through the work first. One should go through the calculations on their own. So there is all kinds of help here, all kinds of theorems can be used here, but we are trying to just do them by hand mostly. So let's do this calculation together. Okay, let's do this. A bit of calculation, but you have to, the more you do, you will find techniques to sort of reduce the calculation, and through them you can find some theorems. But let's do the calculation. So what reductions can you suggest? Anything? Anyone so far? Okay, 3 cube is 22 mod 49. Right, so I'll just write 3 to the 4 also. 3 to the 4 is not so good. Maybe let's write it and see. Uh, no. So 17, you're saying this is 17? 17 is not so bad. I mean, it's better than 22 maybe in the sense of calculation. So 3 to the 4, and let's see. So basically, if I stick with the 17, let's see. Revisit is fine. Does it, or minus 17? Does it give minus 17, right? I don't know. 81 plus 17 is, yeah, minus 17, right? Minus 17 is correct. Right. So that I have to be careful. Okay, to understand. So the remainder is in fact not 17, minus something else, and then so let's calculate and see. So we shouldn't be confused. We shouldn't be making guesses in the sense. I'm sure we are not, but we get 81, and then this 81 is what? So this 81 is 33, right? And then the 33 is what? So 33 you can write as 33 minus 49. That's the same thing. Doesn't that's the same, right? Uh, so this one is minus 17, or is it minus 16? Uh, Something is wrong. What is wrong here? So 32 or something is 32, right? Yeah, 32. That's, either way, so you see it's minus 8. The calculations get me a little. Yeah. No, but that's what we have to do now, right? So we have to get this, and then now we want to calculate what? Now we want to calculate 7 to the power 30, right? Because that's 3 raised to the power 17 to the power 30. How much is this? No, we have to calculate. I mean, we cannot, we have to do the calculations. So we go with 17 square, right? 17 square is how much? Something, how much? 289, right? Yeah, 289. So 289, if you divide by 49, how much is it? 49 into 3, right? Yeah, minus 5. That is good. Yeah. So here the minus was there, but yes, minus, but then we forget that minus because it's power 30. Minus 5. Minus 5 is not so bad, right? Minus 5 is minus 5. It's okay. I mean, this case would be more computational, but no, so that's wrong. I've written. I mean, 17 square is minus 5, right? 17 square is minus 5. And then from here, you again have to work. But it's not like an infinite amount of calculation, right? It kind of reducing. So you have to. So so yeah, what is the next thing that you should do? 15, power 15. Yeah. So calculate and do. So this is your homework. So the homework is to understand this question for 7, 13, and 11. Okay. See what you can do. Okay. Yes. Uh, yeah, but that could again be 1, right? It could be minus 48. Yeah. Actual one? No, the actual one is gotten by just adding 49 enough times, right? You understand, right? I mean, if this comes out to be minus 48, then what is the actual remainder? Actual remainder is 1 in that case, right? Because you could just, that's just, yeah. And this is not, I'm not saying a trick, right? I'm just saying that if you do 49q and someone tells you that this is minus 48, then you want a number here in place of minus 48 that is between 1 and 49, of 0 and 48, right? So what's the best way to do that? Is just to add this 49 here and subtract the 49 here. And this can again be written as a multiple of 49. And here you get the 1. So it makes sense to add and subtract multiples of 49 is what I'm trying to say. So if you do this so just let's leave that for homework. So do those calculations and see how much effort it takes and so on. Okay. You have to do this. What the certain small things that we are missing, and that's why it's taking us a very long time, is so there was a once a long time back, I had mentioned this result, which I'm not telling you have to use. Okay. It's not, so just a minute, I have to plug in the charger. So we were discussing this phi function, right? We were saying that if you take any number a, so we had this Fermat's theorem that it's like a to the p minus 1. If you take a and you raise it to the power p minus 1, then that gives you a remainder 1. I don't think we proved it. But then I stated a similar result when you were trying to sort of understand generalizations of it. So we said that any a, if you raise it to the power phi n, which is the number of numbers less than 49 and co-prime to 49, right? So that would also give you 1, right? I maybe we didn't prove it, but you could apply it in this case, right? So you could say, okay, I will take the 3 and then I'll calculate this phi of 49. Not difficult to calculate. We will know a formula for this. Yeah, I suppose we had done a formula for this, right? But you can even just count it. Yeah, but we had done the formula. And then you get there. Right now, I know we didn't prove this result. We proved the formula for phi n, right? I don't think we proved this result. Well, this result is not hard, not hard at all, but just it takes a bit more language. So you could take that and you can, then that will significantly, simplify your calculations. Do you guys agree? Right? Once you know that, then you will know that multiples of 49 will give you 1. So you could get close to 120 in that way and then small number. So you can use that to simplify. If you don't use, then you do more calculations. That's up to you. It's the same thing. But it's okay. You don't have to use this if you're not comfortable with this, but calculate. That's one thing which we are missing. But one more important thing which we are missing, more relevant, much more relevant thing which we are missing, but you have to do the calculations, is the following. So that's the reason why today I was focusing on finding primes, finding not just prime factors of this, but powers of it. But mostly, while even finding the prime factors, we were focusing on finding it in this way, right? You kind of write the number in a certain way, and then you realize that 7 is a factor immediately. Now, the advantage of this is that now if you want to ask whether 7 square divides it or not, that is the same question as, this is the same question as whether 7 divides 729 to the power 120, not 120, 20, right? So basically you remove that one factor which you observe, that 729 minus 1, right? and you ask this question. Yeah? Now, this question is much easier to answer. Why is it much easier to answer? Again, now so as well, you could, it's easy because simple way, without saying that you can apply polynomials and so on. The simple way why this is easy is because, well, this is just this. Okay, let me just write that expression, right? The geometric progression formula, you could say, or factorization, you could say, is that that quantity is just this. Maybe it's better to write a bit more. 729 square, right? And so on. Sneezing. So you get this, right? So you agree that this is the same thing. Yeah, now that is also we have seen in polynomials, this factorization of x to the n minus 1 is equal to x minus 1 times or geometric progression formula. That. Now you can use that, right? Now you can, now it's not very difficult, right? So now it's, now you see, right? This leaves a remainder. What remainder does this? Now it's much easier. Now this, leaves a remainder of 1 when divided by 7. No doubt about that, right? That's where we came from. This also leaves a remainder 1 when divided by 7, and so on. So what's the total remainder you get? 20. Right? This thing is congruent to, now it suddenly becomes easy to calculate because it's sort of broken up number in a certain way. You've divided and then broken, but all based on some very canonical things. Like you divide by this thing is a very standard thing now because that's how you, and either is you contemplate on this. Point is that this is congruent to 20 mod 7. And so the answer is no. This thing you have to understand and repeat 13 and 11 before I say more things or you. Yeah. So you do the calculations, you can also do like this and it becomes easier. Yeah. Any questions? Any questions, please ask, because now you have to do the rest of the work. You could take a small power than 120 and ask similar questions if you want to. Take 3 to the power 20 and find some prime factor, some big, so say find the big prime factor. I mean, you find and then you see which ones are big and so on. 11 will still be, and then you ask for 11 square in that case if you want. Do it anyhow. Either you do the congruence calculation or you do this thing. Okay. But is it making sense how this method is slightly seems to kind of tell us the more true picture of why that 20 there was the reason, because that 20 was not divisible by 7 was the reason why this was not divisible by 7, and hence that is not divisible by 7 square. That 3 to the 121. Is that making sense? This method is slightly different, right? So now this method and congruence method or any other method or just calculation you see. Yeah. So all these things you see and combine and try to answer the question for 13 and 11. Or you, as I said, take 2 to the 20 minus 1 and do. Or just ask for 2 square. We didn't even try that. That should be the first thing you try. 2 square, 2 cube. And see, yes or no, what you get. Try all the methods and try and see. Okay? So there's plenty of things to try now. Keep trying this and send me what you have tried. Okay? And that's how you progress. This is a very interesting topic which we are doing. You must spend time on this. See. Okay? Yeah, just sit with a blank sheet of paper or something if you want to note if you have noted and try. In a sense that you should have minimal stimulation from outside and more from inside to try and see what you discover on your own that time is what you learn mostly. Yeah. So yeah, small numbers, big numbers, calculations, congruences, this anything you try, but you answer these questions or simpler versions of this. Okay. That's it for today. Okay.